Hi guys, today we're talking about the rate of change in polynomial functions. So our goals today are just to review the concepts of average and instantaneous rate of change, to then determine the average and instantaneous rate of change in polynomial functions, and also a bit of an application of that. We're going to find the equation of a tangent line using the instantaneous rate of change as slope. And to find the equation of the tangent that goes through a given point. So first, we just want to recall what we've learned about the difference between average and instantaneous rate of change. So the definitions, average rate of change is over a given interval, so from x1 to x2. It's the change in y, the average rate of change in y per 1 unit change of x. Okay, so if you get a rate of change of 5, that means on average, between x1 and x2, y has increased by 5 y's per 1 unit of x. Okay, so if you have, let's say, distance versus time, between 1 and 3 hours is 5 meters. That doesn't really make sense, but let's just say it is. Then that means on average, it's distance has increased by 5 meters per hour between 1 and 3 hours, okay? But instantaneous rate of change talks about a specific point. We let it be A. At that point, what is the rate at which y is changing with respect to a 1 unit change in x? Okay, so graphically, the average rate of change is the slope of a secant, so a line that connects 2 points. It's the slope of that line, whereas instantaneous rate of change is the slope of a tangent at x equals a. So the formulas are here for average rate of change. It's just our slope formula, except we're using function notation instead of y2 and y1. And for the instantaneous rate of change, we're focusing here on the difference quotient. Okay, so you take a point very, very close to our desired point A. You just add a little h, so like 0.1 or 0.01. And you put it into this formula, so it gives you a slope very, very, very close to the slope that you're trying to get to. You need to perform this formula at least twice, with h getting smaller the second time. And you need to look at your solutions to see what the slope seems to be approaching. Don't just necessarily take your second answer as the answer. You're looking at a pattern. What is the slope approaching? Okay, so if a third calculation is required, then just do the third calculation. So average rate of change is an exact number, whereas for now, until calculus, the instantaneous rate of change is an estimate. So in this example, we're asked to determine the average rate of change from x equals 2 to x equals 5 in this function. So we need to set up our formula. So the change in f divided by the change in x is equal to f at 5 minus f at 2, all divided by 5 minus 2. So when you put 5 into the function, you get 7. When you put 2 into the function, you get negative 2. And then, of course, 5 minus 2 is 3. So altogether, here you get 9 over 3, which is just 3. So this means a few things. Number one, you can determine that the slope of the secant between these 2 points is 3. So the slope of the secant from the coordinate 2, negative 2, because that's the y value we found for 2, and to the point 5, 7 is 3. So that's one conclusion that we can get from it. If we want to describe it in words, we could say y is increasing, comma, on average by 3 units per 1 unit of x between x equals 2 and x equals 5. Okay, so those are kind of the two different ways that you could describe it, either graphically about the slope of the secant, or kind of more conceptually here. All right, so if we go to GeoGebra, I've set this up for you. You can see visually what's going on. So I've already sketched, you can see here, f at x equals x minus 3 minus 1, cubed minus 1. So you can draw a secant by selecting this line tool, going to line. So you can click the point where x is 2, so that's right here. Just try to make it as accurate as possible. And you can notice here that it's chosen, it says on the very left-hand side there, a is 2 minus 2, so that's right. And then 5 is up here, so you click that as the second point. So you'll notice here it also says b is 5 comma 7. So the equation of the line is minus 9x plus 3y equals negative 24. So if you change that into y equals mx plus b form, you'll see that the slope of the line is 3. So that's the equation of that secant. Okay, so visually, there's the average rate of change. It's going up by 3 for every 1 unit increase of x. Okay, so let's go back to the note. So now the next question is taking that same equation and finding the instantaneous rate of change at x equals 2. So at that point, x equals 2, what is the instantaneous rate of change? So in my first calculation, I'm going to let h be equal to 0.1. Okay, so I have delta f over delta x equals f at 2.1 minus f at 2, all divided by 0.1. Okay, so when I put 2.1 into the function, I get minus 1.729, subtract my negative 2, divided by 0.1, and I'm left with 2.71. Okay, so now I don't know, is the slope 2.7? Is it getting closer to 3? Is it getting closer to 2.5? I don't know. So I need to do another calculation to see what is this slope of the tangent approaching. So now I'm going to let h be equal to 0.01. So I go through and do the same thing. Delta f over delta x equals f at 2.01 minus f at 2, all divided by 0.01. So when I go through and do that calculation, I get 2.97. Okay, so does it make sense that this slope is getting closer and closer to 2.97? No, that doesn't really make sense, because this got from 2.71 and went to 2.97. So I can conclude from this that it's approaching 3. The slope is approaching 3. If you're not confident with that, especially on a test or a quiz, you can go and do a third calculation with h being 0.001, and you will see that delta f over delta x is even closer to 3. So it's going to be approximately 3. So if you need to do a third calculation to be confident, then go ahead and do that. But you can see here that the approximate rate of change is 3. Instantaneous rate of change is 3. Or you could say it appears that the rate of change is approaching 3. So if I go back to GeoGebra, that would be equivalent to drawing a tangent at this point 2. So you can actually go to the input bar and put tangent, and you'll notice all these different commands come up. So we're going to pick x value and function. So you don't have to pick it. I'm just saying that's one of the options. So tangent and then a square bracket. So our x value is 2, comma, and our function is f at x. Press enter. And here it does two things for you. First of all, it draws the tangent line, which is almost the same as the secant. So that's why you would have to zoom out to really be able to see the difference. Or maybe it took away the other line. Anyways, but it also shows you the equation, which is what's most important here. Y equals 3x minus 8. So the slope there is 3. So that means that's right, that the slope of that tangent at 2 is 3. So the tangent at 2 for the function f is 3x minus 8. Its slope is 3. So that means the rate of change there is 3. And that actually is an exact answer. Okay, So here's example 2. We're going to sketch a graph of this function, and then we're going to find the instantaneous rate of change. So to sketch a graph of this function, we need to find the zeros. So we need to go through and do synthetic division. Okay, so the factors, you can see possible factors, plus or minus 1, plus or minus 3, plus or minus 9. So luckily not a lot to go through. So you set up your synthetic division, 1, minus 2, minus 8, 18, and negative 9. Bring down the 1. Okay, and I know that 1 is a factor, so that will work. Okay, so that's your first factor. So you get x minus 1, and then x cubed minus x squared minus 9x plus 9. So notice that we still have a cubic, so we have to keep going to factor it. So either you can do synthetic division again, or you can notice here that it's possible to factor by grouping. So x minus 1, x squared, bracket x minus 1, minus 9, bracket x minus 1. So then you get x minus 1, x squared, minus 9, x minus 1. This is a difference of squares. Okay, and you can collect, since there's two x minus 1s, we can write it as x minus 1 squared. That takes care of both of those. And then our difference of squares is x plus 3 and x minus 3. Okay, so that's just another way to write f at x. So now we can use that to graph. All right, so we have zeros at 1, at positive 3, 1, 2, 3, and at negative 3. Okay, we also know that we have a y-intercept at negative 9. I'm going to go down by 2s here, so 2, 4, 6, 8. So negative 9. Okay, so this is minus 2, minus 4, this is 2, 4. Okay, so this is a quartic that opens up, so we know that its end behavior starts up here and will end going back up. So the 0 of negative 3, that x-intercept has an order of 1, so we pass right through it. Okay, we don't know how far this goes down. It goes down quite far, actually, but it doesn't really matter. Goes through this y-intercept. Now, the order of this x-intercept is 2, so it looks quadratic there. We go down, we come back up, and our end behavior ends in this way. So that is a very basic graph. We can label our zeros and our y-intercept. Sorry. 1, 0, 3, 0, and this is the function f of x. So there we go. So now we want to determine the slope of the tangent at 2. So 2 is right here. Okay, so it looks like it might be some kind of minimum, but it actually isn't. So our graph isn't super helpful there. Because it might look like you would have a low point there, but in actuality, this is just a sketch. Okay, so we want to estimate the slope of the tangent at x equals 2. Now, I can show this to you first in this time graphically on GeoGebra. So this is, in actuality, the sketch of the curve that we just came up with. So notice that it does have a y-intercept here of minus 9, but in between there it goes way, 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 way down to like minus 45. Okay, so the only way you could figure that out is by actually, using calculus, or by just testing numbers in a table of values. And between 1 and 3, you might think that it would have a minimum at 2, but it actually doesn't. It kind of angles this way. So again, you would need to use calculus or just guess and check to find that out. So we can use our tangent function to solve this problem. So at the x value of 2 of f of x, what is the tangent? So you'll see we have minus 6x plus 7 is the equation of this tangent line. So basically we should come to the conclusion through algebra that the instantaneous rate of change is negative 6. All right, so let's go and do that algebraically. Okay, so you need to do it at least 2 different calculations. So first you let h be equal to 0.1. and you do delta f over delta x is equal to f at 2.1 minus f at 2 all over 0.1. Okay, so when you go through and do this, you get minus 5.539. Okay, when you get h as 0.01, delta f over delta x is minus 5.95, actually, sorry, do that. Right, it's 5. Oh yeah, it is. Sorry, I was looking at the wrong thing. Okay, minus 5.9593903. So you can see that it is getting closer and closer to -6. Okay, so you would not conclude minus 5.9. You would see that it's getting closer and closer to the constant of 6. So therefore, we would say that the slope is equal to approximately what we think, -6. So now we get to a question where we want to apply this knowledge. So this is asking us, how can we find the equation of the tangent line? And then we can sketch the line. Okay, so if we go back to GeoGebra, we know that this line should be minus 6x plus 7, but how do we do that algebraically? Well, a tangent is just a line, so its equation is of the form y equals mx plus b. Well, what do we know already? We already know m. That's what we just found. That is equivalent to the instantaneous rate of change. So therefore, m is equal to -6, which is what we just did. And we don't know b, but we do know one point that is on this line. Well, what is that one point? Well, we know it's at x equals 2. So we can sub in that in. So we just need to find y, which is f at 2. Which we know to be -5. Or you can put it back into the function and realize that it's -5. So we use that information back into the y equals mx plus b equation and solve for b. So -5 equals -5 equals -6 for m, and 2 is x plus b. And you can rearrange and solve, and you get b equals 7, which is what we should get. So therefore, our equation is y equals -6x plus 7. Okay, so it asks us to sketch this line. So let's go back to this really terrible drawing that I did. Okay, so that means here you would want to take an eraser, which I will do, and say, okay, I must have made a mistake here because there can't be a horizontal tangent there. There is a tangent sloping down. So that means that this must go down like this and have some minimum over here. Okay, so you can do that line of reasoning. So then you know that it goes through this point, 2, -5. And so you can take a ruler and also connect it to the point 0, 7, because you know the y-intercept is 7. So 2, 4, 6, so 7 should be here. And then you take a ruler and you connect those 2 points. And that is the tangent line. Okay? So you might need to play with it a bit to make your curve look tangent at this point. When you get to calculus, we're going to have such a better way of doing this. But that's the equation of your tangent line. Hopefully it's a bit easier for you to do on graph paper than it is for me using this stylus. So that's basically the note for today. So you're just still using those average and instantaneous rate of change formulas to solve problems. It's just that all of the curves will be polynomial. So just make sure that you can distinguish the difference between the two, the average and the instantaneous, so that you understand that chart fully. You can discuss it at length. You can find and estimate the two different rates of change, and also that you're able to find the equation of a tangent using the instantaneous rate of change. All right, so thanks for watching, guys. Hope you learned lots.